Okay, another going back, touching on the body and membrane transport. One of the huge places for membrane transport, which is both active and passive, is in the kidney, in the nephron, the glomerulus, and the nephron, the loop of Henle, ascending and descending loops of Henle, where you have active transport to reabsorb water back across. And normally the body will spend a tremendous amount of energy pulling salt, actively transporting salt, and creating a gradient to draw the water by diffusion across the membrane and back into the circulating canals and then back into the blood system. Your body filters about 180 liters of water a day. You excrete maybe a liter, so you have well over now close to a 99.5, 99.8% reabsorption rate of water through the kidney, which is extremely important for life because you couldn't lose that much water and still live. Okay, the other part that we're looking at, we're moving into chapter 5, is we're talking about cellular respiration. Now, what we're doing in chapter 5 is we're making micicles. We're showing then, again, another homeostatic mechanism, whereas if the mouse or if a mammal, which is a warm-blooded animal, is cooled, the definition of one of the definitions of a mammal is that you maintain a constant body temperature. This is maintained if you're too warm because of sweating or something along that line, the pig laying in the mud. Or if you're too cold, your metabolism increases. You burn energy. By burning the energy, you create calories, which raises the body temperature. As you move toward hypothermia, you start shivering, which is a very kind of a last-ditch effort to raise the metabolism and maintain body temperature, but it means that you're really well on your way to hypothermia. So what we're going to look at in the lab is we're going to take mice, we're going to measure the amount of oxygen that they use by using a closed manometer system. Then we're going to chill the mouse and measure the amount of oxygen that the mouse uses as its body temperature goes down. This is indicative of using more energy, shivering, whatever, in order to maintain its body temperature. And this is a cellular respiration. And what we're looking at here is by using the soda lime in the container, it absorbs the CO2 that is excreted by the body's metabolic activity. As the sodium chloride, as the CO2 is excreted, the bubble in the manometer moves, so you can actually tell how much oxygen is being used by the mouse, and you will see it go up as the temperature of the mouse goes down. This allows us to get an idea of how much oxygen, mils of oxygen, the mouse uses per gram. And you'll see that the amount of oxygen used because of the energy requirements to stay warm goes up. This again is a homeostatic mechanism, and it works. This experiment works very well. The other thing that we're going to do is you're going to, if you go back to the pH lab number 2, you're going to see that CO2 combines with water to form carbonic acid, and this is with the aid of the enzyme in humans, carbonic anhydrase. And what we're going to do is we're going to measure in the lab the amount of carbon dioxide, or the amount of time it takes for carbon dioxide to change the pH of the solution. But what the take-home message here is that, again, maintaining the body temperature is a homeostatic mechanism, and what we're going to do in the lab is measure the amount of oxygen used to maintain body temperature by the mouse, and we're going to do that by absorbing the carbon dioxide and measuring, again, the amount of oxygen that's taken in. You'll see that the colder the mouse gets, the more oxygen is taken in, carbon dioxide is excreted, which is absorbed, and you'll see the bubble in in the manometer change. Again, a mammal, because the mammal is warm-blooded, it has to maintain a constant body temperature, and it expends energy. Now that is different than, say, a snake or a turtle or a frog, which is a cold-blooded animal, and when they're in the severe cold or in the winter, they bury themselves, and their body temperature literally goes down to pretty much match the temperature of the environment. I think that pretty much answers everything. Let's see if I have any time left or if I've gone over my time here. Hang on one second. I am at 19 minutes and 55 seconds, which means I'm going to